Okay, so welcome back. So in the next lecture, we're going to look at very closely three important reactions. First reaction is a conjugate addition, which I think several of you might have already been exposed to. And the second reaction we're going to look at is enolate alkylation. And this we have, in passing, we have looked at it in some examples, but we'll look at a few more examples. And lastly, we'll look at acylation reactions. Okay. So let's start with the first reaction, which is the conjugate addition. So I'll start with this example or a reaction that has been conducted. So when we take a carbonyl compound typically and react it with sodium cyanide, we have looked at this in several examples. And the conditions I'm going to use are NaCN, HCN, and I maintain the temperature between 5 and 10 degrees centigrade. So, we already know quite well that cyanide can attack and open this up, and eventually you produce the cyanohydrin as the product. Okay, so as expected, if I look at the infrared spectrum of this compound, I see peak around 1700 centimeter inverse, which corresponds to the carbonyl compound. And when I record the infrared spectrum of the product, I see a peak at 3600, which is broad. Okay, and this is basically corresponding to the OH stretching frequency. And I also see a peak at 2250. All of these are in centimeter inverse. And this corresponds to the C triple bond N. Okay, so this we have also looked at prior in the class. And lastly, I see a peak at around 1640, which is quite a weak signal that corresponds to the C double bond C. Okay, and most importantly, this stretching frequency that I see here is absent. Okay, so all of these data show that or suggest that this is the product. They're consistent with the formation of this product. Now, I'll give you one more example. So we take C double bond O and react it with butyl MgBr, magnesium bromide. So this is the Grignard reagent, which we have looked at previously. And the second step is basically addition of water. And again, the similar mechanism is proposed. So you have Bu minus in principle, attacks here and produces the addition product. And you would expect OH, Bu, and this is the double bond. And again, if I measure the IR or if I record the IR spectrum of this, I see a signal at 3600 and then 1640, which is a weak signal, and this is broad, right? And no signal at 1700, which is expected for the ketone. All right, so all of these values are in centimeter inverse. Okay, so this works very well, and this is consistent with whatever you have studied so far or you have discussed so far. But if there is change the conditions a little bit. So the conditions I'm going to use for the first reaction, the cyanohydrin formation reaction, is if I start this reaction at, instead of 5 to 10 degrees centigrade, I start it at 80 degrees centigrade. Okay, so I just put it in an RB flask and just heat it up to 80 degrees. Okay, now I get this product A. Okay, and this product has a signal at 2250 centimeter inverse. Okay, and it does not have a peak at 3600. This is absent. Okay, but instead it has a peak at 1715 centimeter inverse. Okay, So this is all -1. So now what this IR spectrum data suggests is that there is no OH functional group, okay? Because the OH functional group is very, very characteristic, and you will see a very broad signal at 3600. And in fact, sometimes if you don't dry your sample properly, you also end up getting a peak for water, but sometimes you do misinterpret the spectrum. But if you dry your sample appropriately and properly, then you should not see a signal for water under those circumstances. All right. So now the question is, what is this product? Okay. So looking at the data, it seems like, clearly the cyanohydrin is not an option because the OH peak is not being seen. And you see a nice sharp peak at 1715, which shows that the carbonyl compound is still present. Okay. But another clue that we get is that the weak absorption at 1640 is absent. So it seems like this double bond is gone, the carbonyl remains intact, and a cyanide has been added. So based on this data, we can suggest, and of course we can look at other data as well, but just for the purposes of this experiment, we just suggest that we have only, let's say, assume that we only have an IR spectrum to work with, right? Otherwise, we would use things like NMR and mass spec and many other tools to study the reaction or to identify the product. Okay, so based on this, one can propose that the C double bond O remains intact, and this is the product. Okay, now is this product consistent with the structure? So the C triple bond N is still here, the carbonyl is still there, and there is no hydroxyl group, so you don't expect a peak at 3600. Okay, so this is not a single example of this. So let's look at the Conjugate addition. Now we are going to change the conditions a little bit, just like we increase the temperature in the case of the sodium cyanide reaction. What we will do is we'll add butyl magnesium bromide, but the difference here is we will add 1% of copper chloride. Okay, and the second conditions remains the same, which is basically work up with water. And now I get this product B. Okay, now let's look at the characteristic signals of product B. So here again I see signal at 1710, and 3600 is basically gone. All right, and just to be clear, the C double bond C weak signal is also absent. All right, so based on this observation, keep in mind we'll get to this later, but the only difference in conditions is the addition of 1% CuCl. And the product that is proposed is Cn C double bond O. So as opposed to the original product that we would get, which is this. So therefore, this compound is not formed under these conditions, but it is compound B that is produced. Now, before we get into some details, let's look at the arrow pushing mechanism. The arrow pushing mechanism is as follows. So I start with C double bond O, this alpha beta unsaturated. So by the way, this is called as the alpha position. This is called the beta position. So whenever you have a functional group which is attached to a carbon, let's say this is CH2 and this is CH3. This is referred to as the alpha position. This is beta, and then you have gamma, delta, and so on. Okay, if you have a longer carbon chain. So these are important positions because they sort of play a role. Sometimes they are better at accepting electrons or accepting radical or reacting as a radical and so on. So in this case, this is an alpha beta unsaturated carbonyl compound. Okay, so these are important compounds, very important synthetic intermediates. We'll look at it not just here, but throughout the next few years that you will be studying chemistry. So now coming back to the arrow pushing mechanism, so we have Cn minus, it attacks on this here, and then this moves here, and this moves here. Okay, so the product that is produced, the intermediate that is produced is this. So let me just number this so that it's easy for us to follow. We'll follow the same system: 1, 2, 3, and 4. And so O minus. So let's draw out the skeleton first. There's a new bond between 1, 2, 3, and 4. So there's a new bond between carbon 2 and carbon 3. There's a new bond between carbon 2 and carbon 3. And then there's a bond between 4 and Cn. Okay. And rest of the molecule remains the same. Now, if this picks up proton, basically from water, then you have, it's like an enolate, it picks up this proton, and the product that is formed is C double bond O, Cn, and there's your new hydrogen that is produced, and the numbering is 1, 2, 3, 4. Okay, so this is the formal arrow pushing mechanism. I would urge you to draw this out for the similar mechanism for the 1,2 addition as well. Okay. Now, with that, let's look at some examples. I'm not going to go into an exhaustive set of examples, but I'm just going to give you like 2 or 3 examples. So, the first example is I can also start with alpha beta unsaturated ester. So, this is the alpha position, this is the beta position. And now the reaction of cyanide under certain conditions can occur, and you get the corresponding cyano derivative. So let's keep the same numbering: 1, 2, 3, 4. So this is carbon 4, 3, this is 2, and this is 1. Okay, so now here is your OET, O minus, and that's the enolate, and here is carbon 2, and this is oxygen 1. Okay, so this is going to be your intermediate, which then picks up a proton to give you OET Cn. Okay, so this is possible. You can also have the reaction of different kinds of nucleophiles. We will look into that a little bit later. But the interesting reaction that I would point you out to is the reaction of benzene, so which we have looked at quite in detail in the earlier part of the semester. But let's say you start with this type of a compound and you add AlCl3. So if you recall, this is the Friedel-Crafts reaction, and the product that is formed is this. Okay, so draw out the arrow pushing mechanism for this, when you get time, and get yourself familiar with this whole reaction. Okay, now let's try and understand some of the aspects of reactivity of these conjugated olefins or conjugated carbonyl compounds, or these alpha beta unsaturated carbonyls. So the first sort of important aspect in the reactivity of or the structure of these compounds is that what we normally look at is basically, since there is conjugation, we can look at resonance forms. Okay, so if we were able to draw out this resonance form, which is the enolate form, so you have O minus, and then you have a full-fledged positive charge on carbon. So one could argue that this carbon over here is going to be electron deficient. So this is an electron deficient center. Therefore, it's not unreasonable to expect that this carbon is actually a reactive center. So let's just revise that. This is called the alpha position, this is called the beta position. Okay, so there is a fair amount of polarization that occurs, and this is going to contribute to the unique reactivity of these types of compounds. Okay, now can we detect this polarization through spectroscopy? Okay, so one of the important spectroscopic tools is NMR. So here, if I, for example, just take a traditional olefin such as this, then the C13 NMR spectrum of this shows that, this over here appears at 119 ppm, and this carbon over here shows up at 132 ppm. Okay, so these are all values in ppm. Now, so just to sort of put this data in perspective, normally if I take a functional group and if I keep adding electron withdrawing groups, the electron cloud around the nucleus sort of goes down. Okay, and once the electron cloud goes down, let's say I take the values of 0 to 200. So the more electron deficient it is, the higher the ppm values. Okay, so therefore, if I take a carbon which has some, this is only a very rough analogy to show. So if I take this is the electron cloud around this carbon, then as the values go up, one of the indications, not the only indication, but one of the indications is that the electron cloud around this is less. So as and when you add more electron withdrawing groups, the values of the chemical shift goes up. Okay, and this is also called as de-shielded. So this is more shielded and this is de-shielded. Okay, so this is also another terminology that is frequently used. Nevertheless, coming back to these compounds, so now if we look at the same sort of framework, but the only difference here is I'm adding a C double bond O instead of a methyl group, I'm adding a carbonyl compound. So this carbon over here shows up at 143. Okay, whereas this carbon over here shows up at 124. Okay, so these values are ppm again. Okay, so you see here that if I compare 119 and 124, I see that there is an increase or a shift towards the more de-shielded region. Similarly, if I take this carbon 132 and 143, there is a substantial de-shielding that is going on. So this spectroscopic data again supports that the resonance form that we looked at in the previous slide. It shows that it sort of suggests that this kind of an electron deficient carbon is actually present. Now, we will spend a little bit of time and look at molecular orbitals. Of course, you will realize that it's going to take a little bit of time to draw these out, but nevertheless, we will try and draw them out. I would urge you to look at the textbook. Again, there's a chapter on this. This is chapter 22 in Claydon, which talks about conjugate addition. You may also look up other chapters, other textbooks that we have in the list. But Claydon is a really nice book. Okay, so I'm going to try and draw this all in one slide, which is going to be quite challenging, but let me nevertheless give it a shot. Okay, so the reference set of molecular orbitals that we're looking at is actually 1,3-butadiene. Okay, so 1,3-butadiene has the following structure. Now, so if we just going to draw all of them over here. Okay, so this is my framework for 1,3-butadiene. Now I'm going to draw out some orbitals, but they are going to be, the size of these orbitals are not accurate, and so there may be some differences because of my drawing, but I would again urge you to look at the text to get the correct number or the size. Okay, so this is the first set of orbitals. Now, if all of them are the same sign, then this is going to lead to the most favorable, sort of overlap. The second situation is that, two of them are going to have the same sign, and the other two, for example, are going to be overlapping, and then there is a nodal point, and then there is these two that are going to overlap. So this is the second level. All right. The third level is you're going to have these two sort of the same sign, and this is going to be the opposite sign. Okay. So that leads to the empty orbital, because there are only 4 electrons in butadiene. And the last one is where, all of them are mismatched. Okay. So there's no sort of overlap. So this is here, this is here, this is here, this is here. So this is fairly straightforward to draw out. Okay. And now just to recall, this is the lowest unoccupied molecular orbital, and this is the highest occupied molecular orbital. Okay. So now what I'm going to do is I'm just going to draw similarly the sort of picture for acrolein. And acrolein, maybe I should just draw it out on the next page. So this is for 1,3-butadiene, and if instead of the carbon, if I have an oxygen, this is called as acrolein. Okay, so let me just draw out the acrolein in the next page. But suffice to say is that because of the higher electronegativity, by the oxygen, there's going to be the levels are going to go down. Compared to this, the levels are going to go down. Second thing is that what you can expect from previous discussion is that there's going to be a fair amount of distortion and asymmetry because of the presence of the oxygen. Now, so if I draw out the levels for acrolein, again, I'm just going to draw this out in the following manner so that it's easy for us to follow it, and then we'll draw out the orbitals. Okay, so now again, like I mentioned, these are each of them is one energy level, and you have 2 electrons here, 2 electrons here, and then that's about it. So keep in mind that when we're looking at the molecular orbital picture, we always look at the pi bonds here because they are the most reactive. Okay, so now coming back to this MO picture, so we have a lobe over here, and then over here, and then over here. Okay, so again, I'm not drawing this to scale, but the two important features of this I will just tell you shortly. But this is here, 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 and here. So here all of them are going to be favorable overlap. Okay, and as you know, the second one is going to be 2 bonds are going to be favorable overlap. Now coming to the third, which is the LUMO, which is the lowest unoccupied molecular orbital, the picture looks something like this. The slightly smaller lobe over here, there's a slightly smaller lobe over here, and then there's a lobe for the oxygen. Okay, now we need not worry about how these orbitals have been calculated, but the important point here is that you're going to have the largest coefficient is going to be at this beta position. This is the orbital with the largest coefficient. Okay, so what this means is that the LUMO, which is the lowest unoccupied molecular orbital, has the beta carbon as the lobe or the orbital which has the largest coefficient. Okay, and lastly, to complete the diagram, we have the last orbital to look at. And here again, we're just going to draw out the orbital and show you the signs. The sizes of these orbitals are going to be something that you need to look up and find out for yourself. Okay, so they're all opposite signed, and so that completes the molecular orbital picture for us. Okay, so there are several important points here. Number one, there is distortion. So some lobes are going to be larger and some molecular orbitals are going to be smaller. Number two is that there is an indication of polarization because of the electronegative oxygen. And the third point is that the LUMO, which is in this case because it's an electron acceptor, the LUMO becomes one of the most important orbitals to look at. And the LUMO has the largest lobe on the beta carbon. Okay, so now this sort of helps us understand, this reactivity in terms of orbitals as well. So now if I am looking at this picture again with oxygen over here, now here is your double bond and here is the C double bond O. Now this is as we discussed, this is the LUMO where you have, this kind of an arrangement. And now if, for example, a nucleophile, say C double bond N, has its electron cloud in this manner, and obviously it has to orient itself in the correct way, but it can attack here, and once it adds the electrons to this lobe, then there's going to be a movement over here and you form the enolate. So this is the new bond, C triple bond N and O minus. Okay, so therefore this is the new sigma bond that is formed, and this pi bond is actually going to be broken. This carbon-carbon pi bond is also going to be broken, and you generate the enolate. Okay, so this sort of gives us the perspective about how these reactions can actually occur, and it provides a framework for us to understand the reactivity of alpha beta unsaturated carbonyl compounds. In the next lecture, we will look at how to explain some of the observations that we have seen in terms of why one product is formed over the other.